Hello, we're happy to have you back with us again in our Crystal Clear Electronics 2 videos. Today we're diving into a really exciting topic, but first let me introduce you to the presenter of Chapter 21, David Kulchar. He was already working on embedded systems development while studying electrical engineering in university. Currently, he works in his own company, where hardware and software development and industrial automation are commonplace.
Welcome to the next chapter of our series. Barabás Sebestyén will help us to understand simple real-time operating systems in more depth. Barabás is currently studying computer science in Szeged and is a member of the BME Formula Racing team's electro crew. I think that the topic of operating systems is exciting because it gives us an insight into the basic functionality of more complex systems.
In this chapter, we will focus on the theoretical background of how operating systems work. To give you a little motivation to get through this topic, we'll give you a taste of what's in store for you in Chapter 22, where you'll learn about the topic through practical examples.
Come, let's sit at the table.
In one of the examples in Chapter 22, we implement two tasks. We did this with two different parts of the program, but not just in any way. One function is the LED running light. This is very simple. It is just a matter of switching one of the four LEDs on or off every second. The second function is to read the temperature from a thermometer IC and show it on the display for 3 seconds, then draw a circular arc for 2 seconds. The circular arc increases or decreases every 10 degrees. Oh, and of course the point is that we want all these functions to work as independently as possible, so our goal is to ensure that the LED running light doesn't stop while the temperature program is running or while the arc is being drawn. You'll notice that the running light really doesn't freeze, regardless of the other functions. An LED always turns on and off every 1 second, no matter what's happening on the display. A little description of the program is given in Chapter 22.
As we want to do more and more complex things with our digital systems, the programs that run on them have become larger and more complex. More complex software usually involves more people working on it, and parts of the program and the elements written are likely to come from more than one source. The program itself can consist of several parts, each of which is a standalone program with a task. For example, we can have a program part that reads data from a peripheral and processes it. These can be written efficiently without worrying about what other tasks your microcontroller has to do, but concentrating only on that one function as if nothing else existed.
Operating systems, or OSs for short, were developed to help such complex applications to coordinate and interact with parts of the program. The parts of the program run simultaneously in parallel, or at least the programs themselves see it this way. What do you think? What task does a basic OS have?
The first and most important task is to make sure that the different parts of the program, also known as threads, run seemingly in parallel, simultaneously, so scheduling and thread management are needed. It's the program's task to do this, but the programmer must be aware of the overall operation of the OS. Secondly, communication between program parts and proper memory allocation must be ensured. Last but not least, the management and allocation of other common resources are also an important task of the OS. These could be network management, file management, for example from SD cards, USB management, or the management of other hardware devices.
There are many different operating systems, and they are designed for different tasks and systems. At one end of the scale are operating systems for powerful hardware, such as Linux or Windows. These provide all the features an OS can offer, but they are large and complex, requiring significant computing power and a lot of memory to run.
On the other hand, there are simple schedulers for microcontrollers, such as FreeRTOS. These require only a few kilobytes of memory in the simplest configuration and provide only scheduling and the minimum required services. In this chapter, we will of course only discuss the basic functionality of the simple OSs. To make the topic a little more interesting, I will approach the subject from a slightly different angle. Let's take a simple programming situation and look at how it can be solved in different ways and different methods, starting with the simplest. Let the task be to receive data continuously on a serial port, which we have to read. Every 100-byte packet of data, we have to call a processing function. Then, this happens cyclically. We have to keep reading the data, then processing them. The point here is to read the data. We don't know anything about the processing, that is written by someone else. Barabash, what's the simplest solution to this task? Can you show us?
Of course, challenges like this are simply too good to miss. Let's look at a simple implementation. Here on the screen you can see a so-called pseudo-program, which contains no real program instructions but a description of the corresponding steps that are easy to understand. The program first initializes the peripheral to be used, which is a serial port. This is followed by our main loop, in which we wait for a byte to be received. When a byte is received, it is read and then stored in an array. After this, we check whether we have 100 bytes of data available. If so, we call our processing function on the existing data packet. After processing, we adjust the required pointers and start the loop all over again.
This may be a good solution, but do you see any problems with it?
Yes, sadly this example has two problems. First, the processor can do nothing but wait for data. Second, we don't know how long the processing function takes to run. It's possible that by the time the processing routine returns and resumes reading the data, some incoming bytes have been lost, resulting in a break in communication. There are several ways to solve this, but since we are talking about the operating system, the next step is to use interrupts.
That's a good idea. Let's continue with interrupt requests. To do this, let's first clarify what is the context in the world of microcontrollers. When the code is running, the microprocessor stores in its internal registers the current position of program execution, as well as other data needed for processing. In addition, there are variables used in the program which are stored in specific locations in memory. Together, these form the current state of the program, called the context. We can read this state, for example, with the debugger, and then examine or even modify it when debugging the program. So, if we save this state and restore it later, the program will continue from that point. Context switching is an essential part of the interrupt mechanism, or IRQ for short, which is found in all processors. It is a special mechanism that can interrupt the program execution in response to an event, almost anywhere and at any time, and store the current state. The event that causes this can take many forms. For example, a change in an external logic signal on one of the microcontroller's legs, or a change in a peripheral can also trigger an IRQ. Back to our example, if a byte arrives at the serial port controller, it can generate an IRQ and interrupt the execution of the program. For this to happen, the interrupt controller of the microcontroller and the peripheral handler must first be properly configured. After the interrupt controller interrupts the current program, execution resumes from another memory address, meaning another procedure or function starts running. This function is called an interrupt handler. In our case, if data is received on the serial port, this function will serve as its interrupt handler. We must write the body of this function and set it to be called when a byte arrives. When our interrupt handler has finished running, the originally interrupted context is restored through a special mechanism, and the program resumes running from the same place where it was interrupted. If we want to be precise, the context will not be exactly the same as before the interrupt, because the interrupt handler can write to memory, which is the whole point of its operation. The interrupted program will see that the value of some global variables have changed. Therefore, our program should be rewritten to consciously prepare for this. Let's look at the example with Barabash, now written with interrupts.
So now we will have an interrupt handler function, which will store the data. To do this, we will use several containers. These will be complex structures. Each container consists of a 100-element array and a flag. This flag tells the program whether the array has been filled with data or whether all data has been read from it. When one container fills up, data collection continues in another, and the previous one is handed over to the data processing function. When the flag is in the empty state, it signals to the interrupt function that data can be written into the storage. After the last byte has been written to the store, a single final write will set the flag to the full state, letting the function know that it can now access the data, which will not be changed in the background. When it has finished reading all the data, the processing function sets the flag back to the empty state. In the program, data scanning and processing are separated. The processing is done in the main function, while the data is read and stored in the background by an interrupt function. Here, the main program does not have to worry about timing, it does not need to rush the processing. Other tasks can be performed by the processor, so it is no longer limited to just one task. All the main program has to do is check from time to time whether the complete data packet has been received, and if so, start processing it. When a byte arrives on the serial port, the main program is interrupted for a moment, the interrupt handler reads the data, and the main program continues running. However, this change is not noticed, only that the values in the data buffers, including the flag, appear to have changed.
This is a very important moment. Let's look at this in detail. An interrupt can cause the main program to stop running between any two machine code instructions. A single machine code instruction can, for example, read a byte into memory or add the values of two registers. These can no longer be divided, so they are called atomic operations. For us, this is important because of the handling of the data stored in memory. When we refer to a number in a higher level programming language, accessing or modifying it may not correspond to a single machine code operation. For example, on an 8-bit processor, reading a 16-bit integer requires two machine code instructions during which an interrupt can occur, potentially modifying the number being read in memory, resulting in an incorrect value. Even a simple increment involves several machine instructions: reading a number, incrementing it by 1, writing back the number. If the number changes due to an interrupt during this process, it can lead to a malfunction. Exactly which instructions are atomic depends on the processor. For example, on 32-bit processors, reading and writing a 32-bit integer is usually atomic if the number is stored at an address divisible by 4, since 8 bits are stored per memory address. So if you want to take advantage of this, you have to be careful. However, some instructions, such as 8-bit reads and writes, are always atomic.
In the interrupt example, we use this. As I mentioned earlier, each of our composite data storage units has a flag that is itself atomically writable or readable. When it is in the empty state, the interrupt function can write data to it, but the data must not be accessed from the main program, only the state of the flag must be read. When the interrupt function has finished filling the memory with data and no longer accesses it, it sets the flag to full with the final write, allowing the main program to safely read the data. This is independent of when the interrupt occurred during the main program's execution. Since reading the flag is an atomic operation, its value is guaranteed not to change during processing. When the main program has finished reading all the data, it sets the flag to empty. This procedure ensures that no incorrect data is read when complex data is shared.
To summarize shortly, the main program and the interrupt handler communicate with each other via a readable flag, which is written using an atomic operation to synchronize data access. This synchronization is crucial in any program where parts of the program run independently of each other. In the example above, this is the main program and the interrupt handler. Of course, there are other ways to synchronize. For example, the main program can disable receiving interrupts for a short period of time, allowing it to safely read from or write to memory. A disadvantage, however, is that no interrupts will be handled during this time, so such parts should execute as quickly as possible. Going back to our example, the main program runs in an infinite loop and can perform multiple tasks in succession while data is being read in the background. Multiple tasks means that different functions are called in sequence to perform different tasks. Each of these must be written to execute and return relatively quickly so that the main loop can run the other tasks. This is sometimes inconvenient. Some tasks must wait for other parts of the program to run or for external data, while others simply take a long time. Schedulers, the basis of operating systems, were invented to solve this situation. So, what is a scheduler and what are its main tasks?
In the interrupt example, we saw that you can interrupt the execution of a program anywhere except during atomic operations and store the context, and the program can later resume by restoring that context. If we develop this idea further, we can make a system where we can start several parts of a program and then interrupt them according to our task and store their context in different locations in memory. These contexts can later be retrieved and restored at will, and our program will continue running where we left off. These parts of the program are called tasks or threads. If you quickly change the context between these program parts, it appears from the outside as if all of them are running simultaneously. As a result, the threads behave as if they are running continuously, although their timestamps occasionally jump. For this to work, there must be something above the program threads that decides when to run each one, resets their context, and can interrupt execution at will. We call this program the scheduler. It is the basis of all multitasking OSs.
Finally, we have arrived at operating systems. In our next video, we will introduce the basics of OSs and their functions.
Moreover, you will hear more about the main services that operating systems provide. See you in the next video. Bye!
Bye!